Good afternoon. I'm here to talk about the year in .NET security, all the things that have made my hair get more gray and stop me giving up smoking. My name is Barry Dorrans. I am the security PM for .NET, ASP.NET Core, Aspire, basically everything that falls underneath the .NET umbrella, plus little bits of NuGet, because NuGet is very important in our supply chain security story, and various other random things that I have picked up along the way and I can't pass off to anyone else. So I'm the person that gets calls at 1 a.m. in the morning. I'm going to talk through all the CVEs that happened over the last 12 months in .NET and ASP.NET Core. But before I get into that, I want to ensure that we have a good idea of what the vocabulary is. For people that are dealing in security every day, you're going to know all of this, but most people aren't. Lucky you, you sleep better than I do. So let's go through the terms that I'm going to use as we go on. First off, we have a CVE. CVE stands for Common Vulnerabilities and Exposures. It's the standard for how vulnerabilities get reported to you, the end user. And it's the standard way for identifying them. They all have the same sort of format of ID that you can search on the CVE site. Everything looks the same, so it's all nice and standard, and you can compare and contrast if you feel the need to. Next up, we have how things are scored, which is CVSS, the Common Vulnerability Scoring System. Now, if you read the documentation for CVSS, it calls out that it's not a measure of risk. Just because something has a high score doesn't mean that you're at risk or that you need to immediately run around and patch. I know that feels counterintuitive because a high score where everything is red usually means that you need to panic, but it's not necessarily the case. The scores are calculated from exploitability and impact metrics. So exploitability metrics are the vector, whether it comes over in a network, an adjacent network, whether it's local or whether you actually have to have physical access to a machine, the complexity of an attack, low, medium, and high, privileges, none, low, high, where you're running as root, user interaction, none are required, scope, which is changed or unchanged. A changed scope means that it's hopping off the machine that has the vulnerability and touching other machines, for example, a server-side request forgery attack. Confidentiality starts touching into the impact matrices. It's the CIA triangle of confidentiality, integrity, and availability. And the important thing to know is most of these things are aimed at applications. CVSS is a good way to measure the risk of an application. Trying to apply it to a framework becomes a little bit more difficult. Because we don't know how your application is written, we don't know whether your application is going to be vulnerable to an individual CVE or not. So what we do is we score based on the worst possible case scenario, which is why we had a 9.9 for ASP.NET this year. Sometimes we will look at the way code's written in Azure, and we'll take that as a decent baseline. But we are basically trying to think of the worst possible thing that can go wrong if an attacker exploited this vulnerability in one of your applications. And then we have CWD, the Common Weakness Enumeration. This is a list of reasons why the vulnerability was there. It's a list of common software and hardware weaknesses that a developer introduces when they're writing code. So you may have a buffer overrun, you may have lack of validation on input, that sort of thing. And we try to squeeze our vulnerabilities into that list as much as we can. Sometimes they don't fit because, again, we're a framework rather than a piece of an application code. And so sometimes it just gets incredibly odd. So this is a list this is a screenshot from the CVE website. You can see the CVE number, you can see the score, which is in red, even though it's not a risk rating, and I will underscore that again. You have the vectors, which is how the score is calculated, and then at the bottom you have a list of the affected software configurations. all very exciting, and you can go away and look up each of .NET CVEs and see what the scores are, see what was affected, and this is basically how you try and assess what you're going to do about a vulnerability. So now we've got that out of the way, let's go through the last 12 months in our own vulnerabilities. In the last 12 months, we had 84 reports to the MSRC, which is the Microsoft Security Response Center. They're the people that it used to be email, now you have to fill in a form online. They're the people that you tell that you have what may be a potential vulnerability. Out of that, we had 12 CVEs, and the fun part of my job, I paid out a total of 93,000 American dollars, which was nice. I like doing that. The highest bounty payout that we made this year was for 65,000, and the lowest was for 3,000, which was an issue in our docs. Our bug bounty program covers our documentation. If you see something in our documentation that has a vulnerability, is not demonstrating security best practice in the code, tell us. I might be able to write you a check. So that may sound low to you. The thing is, we have a reasonable number of MSRC reports, but a lower number of CVEs. Not all the things that get reported to MSRC get CVEs. Some of them just are invalid. It's not an actual security vulnerability. Some of them are just plain old bugs. Some of them we can't reproduce, or the code that the person has written is in itself vulnerable and it's not a property of our framework. We issue CVEs for medium CVSS scores and above. And we issue CVEs for when you, the developer, have to take action. For example, we had a report of a vulnerable GitHub action in one of our repos. You don't have to do anything about that. We changed it, we updated it, we secured it, so it doesn't get a CVE. It did get a bounty payment in this case. So the two things aren't necessarily linked. And of course, there are more security fixes that are made behind the scenes where we find our things internally. Some things get rated low, which then become fixed in next version bugs. And that will happen, when you pick up .NET 10, you're going to get a whole bunch of security updates that were marked as fixed in next version. So here is page 1 of 2 of the .NET CVEs. I am not going to go through all of this. It's all incredibly boring. There's the first 6. And then there's another 3, so there are a total of 9. Hurrah! And for ASP.NET, we had 3 this year. Vulnerabilities by type. We had 4 remote code executions, which are the ones that keep me awake. We have 2 denial of service, 1 spoofing, 3 elevation of privilege, 1 security feature bypass, which is that high-scoring ASP.NET one, and 1 information disclosure. In terms of score, we had 1 medium, we had 9 high, and we had 2 critical this year. So now I'm going to go through the .NET CVEs. I want to make an important note here because I will link to the changes in code on GitHub. The person that wrote the fix may not have written the vulnerable code. There's no way to link the two together. I don't look for who wrote the vulnerable code. That's just not necessary. The important thing is getting the fix out. So if you see a fix that's been checked in by someone in GitHub, you cannot tease them for having written the vulnerable code in the first place. So we're going to go through all our 9 .NET vulnerabilities. The first one was an information disclosure, which is CVE 2025-55248. This was in the SMTP client built into .NET that we have said is deprecated. Please use something else. Please use something else. What happened was, even if you had told the SMTP client to use SSL, in some circumstances, if a server didn't support SSL, it'd go ahead and send things to that server, which is an obvious bug. That means if an attacker was sitting between your application and the SMTP server, they could see the contents of the email flowing, and that's good old information disclosure. The fix here was to add the check for use SSL, so if a mail server said, I don't support SSL, it just exits out and doesn't go any further. Next one is a denial of service attack. This was in MS Build, which falls under .NET for the terms of CVSS and reporting. This is due to us not thinking like Linux developers sometimes. So MS Build uses a whole bunch of temporary directories. It uses a fixed directory name and a predictable path. So what an attacker could do is write to the temp directory using that predictable name on Linux, because on Linux, the temp directory is rewritable by everyone, unlike on Windows, where you get a user-specific temp directory. So if you did that, and the attacker had written the directory and locked it down so only they could access it and your user couldn't access it, MS Build would try and then fail, which is a denial of service for your builds. So the fix, and this is one of the things that you can do at home. There is a new API that's been in since .NET 7, I believe, which is directory create temp subdirectory. What that does is will create a subdirectory in the temp directory and lock it down to your process user. File.getTempPath and then creating a directory within that does not do that. So if you are looking through your code, have a look for file.getTempPath and see if directory.create_temp subdirectory works better for you. You will avoid all sorts of fun and games on Linux. 30399 is a remote code execution attack. The attacker could exploit the vulnerability by placing files in particular locations, leading to unintended code execution. Now, this one was interesting. It's a very rare case where a .NET application hosts, or sorry, a non-.NET application hosts .NET within itself to enable scripting, and they instantiate it via COM or C++ CLI or some sort of common hosting core CLR within themselves. Core CLR in that circumstance didn't look in the right places to load all the .NET assemblies that it needed. It just looked in the current working directory. So you could drop something that matched the assembly name and API, exposed API points of a .NET assembly, and it would get loaded in this circumstance. So that's fine, that's code execution, but where does remote come into it? Well, you can run applications off another machine, you can run them off a network share, so that's where remote comes into this. So the fix for this was we removed a fallback path inside all sorts of weird internals in comhost.cs, where if you didn't have a deps.json, it caused .NET to fall back to the current working directory, and that no longer happens, so it's fixed. We have a spoofing vulnerability up next, 26646. The download task in MS Build allows you to specify the file name of the file that you want written to disk. Unfortunately, the content disposition header was also used as a way to generate a file name from the web server you're trying to download stuff from. And of course, content disposition, if you are connecting to an attacker's web server, can be set to whatever you want, including things like not just file names, but directories as well. So this is lack of input validation and also just not doing the right thing here. If you specify a file name in the build script, use the file name. So allowing the server to specify the file name gets categorized as spoofing. And the way that you fix this is don't ever use the context disposition header to allow generation of file names on your local file system. This is down to treat responses from any HTTP request as untrusted. And if you do have to use the file name from content disposition, make sure it's just the file name. There are APIs in .NET that will take a path and just extract the file name. Remember that content disposition, even though the standard, the RFC for HTTP says, no, it shouldn't do this, you can put directories in there. It's an invalid response, but no one filters on those because you have to be forgiving in what you accept. So if you need to do that sort of thing, make sure you're only picking the file name up. We have another elevation of privilege here. Again, dotnet on Linux. This time it's NuGet. The restore operations, we're using temporary directories to store a generated deps.json file. And as I've said previously, the temp folder on Linux is world readable and writable. So an attacker could sit there, watch for this deps.json file being created, and then if they can exploit it fast enough, they can write their own bits into deps.json and cause their own code to be loaded. So the fix, like before, directory.create temp subdirectory. Please go check all your code. Next up, 21172 is a vulnerability in another component that we take from another team, which is the Microsoft Debug Interface Access SDK, MSDA. It had a remote code execution. Dump files are weird things to parse. We use MSDA to enhance our dumps before sending them off to Windows error reporting or off to Azure. You can get nice stack traces out of it. The fix for us was we just took the next version of MSDA that had all the fixes. This sort of is analogous to supply chain security, except we know who we're getting the supply from. And it basically boils down to make sure that all your dependencies are up to date. However, a lot of attacks these days seem to be getting common dependencies, uploading something that has malware or some sort of undesirable effect in the dependency and hoping. If you are automatically pulling in your dependencies on day one, you may be at risk to that. So you have a choice here. You either go and validate that the incoming dependency is what you think it's going to be, that it's been properly released, you check the signatures and all the rest of it, or you give it a couple of days to bubble under to make sure that it's not an attacker that has released this update, because it'll be hopefully pulled within a couple of days. If you're using Dependabot, you can tell Dependabot to wait for a couple of days before telling you that there is an update. Next, another remote code execution, 21171. This was glorious. We use a lot of unsafe code in .NET, much to my annoyance. There are some places where it's unavoidable. There are some places it's there for speed and scalability. I am, of course, of the opinion that security trumps speed and scalability. However, that's not a realistic viewpoint for the rest of the team and probably for yourself. There was unsafe code in convert.toHexstring that calculated a buffer length incorrectly, leading to a buffer overflow. So buffer overflows allow an attacker to write to memory they should not have access to. And in the worst possible case scenario, they could write to an executable bit of memory, which something else then calls into, and that means remote code execution. The fix was changing a greater than to a less than. Yeah, so that was great. That was a community contribution. It was a community report. Unfortunately, it was in a GitHub issue and not through MSRC, so I couldn't pay out for that one. So check your maths, fuzz your APIs, and stop using unsafe code. Another remote code execution, we removed binary formatter. That is my ongoing largest success that I will continue to be happy about long into when I retire. It was replaced with NBRF, which I used to think stood for not binary really formatter, but it stands for .NET Remoting Binary Format. And we had a reader for that. And there was remote code execution due to a bad assumption around types. And so we have an access violation, which again, like a buffer overflow, means you can touch memory that you're not supposed to touch. And then we have remote code execution. So it was down to how IEnumerable was used. You can see the description there. And basically it boils down to when you're expecting a type, don't assume it's going to be the type, actually validate that it is the type you're expecting. And finally, we also had a classic denial of service in NRBF. NRBF documents can contain jagged arrays. You could send a tiny jagged array of about a couple of K, and it would allocate gigabytes. if we were being really silly. We had a 90-byte payload that would allocate 50 gigabytes on the server. This is obviously a denial of service attack. And the fix for this was completely rewriting the jagged array handling, which was a great piece of effort by the developer involved. Then we have 3 ASP.NET Core CVEs. The first one is an elevation of privilege, where we have email confirmation links treated the user ID in the confirmation link as trusted and automatically signed the user in without asking for the user's password. A little bit weird. But you know, this meant that if an attacker had gotten hold of a confirmation link that was unused from a user's email, they could click it and immediately log in as that user, just from confirming the email address. So now we ask you for your password again, and we don't let you go through the confirmation process until you've entered your password. Then we have a denial of service in HTTP 3. It had an unbounded memory growth bug, which is also reminiscent of a slow loris attack. So you could say, I'm going to send 100 megabytes, start sending stuff, and stop at 99 megabytes. The timeouts that we have for that sort of thing in place didn't work in this scenario. So you would have 100 megabytes allocated, and it would be sitting there waiting as long as the connection was open for that last byte. So we made changes to how HTTP frames are parsed, making it clearer that, you know, it's parsed on remaining length, and adding support for partial frames, which is one of those things in the spec that no one really wants to ever use, but it helped in this scenario. And then the last one, the biggie, the 9.9 that everyone got excited about. I was excited that we had a 9.9. Everybody was like, well, hold on, how do I know whether it applies to me? And I'll come to that in a little bit. This was an HTTP smuggling request. This is a classic type of attack. We were incorrectly accepting new line characters in chunk extensions, the HTTP extensions that no one ever wanted. We changed the parser to reject these requests. Now, the reason it's a 9.9 is because of this whole worst case scenario scoring system. We don't know how you're using our stuff. If I had gone through scenarios and said, well, this one is a 9.9, this one would be a 7, this sort of circumstance would be a 5. If I didn't list your scenarios, you might make the assumption that you're safe when I don't know whether you are or not. It's because I don't know your scenarios. That's why we go with a 9.9. This all boils down to, if you're adhering to an RFC, you should be watching for must and should clauses. Should is an indication that the logic there could be undefined. May is even worse. That's definitely undefined. It might work, it might not. Whilst we could make Kestrel strictly adhere to the HTTP specs, most browsers or agents or IoT devices don't adhere to the specs. So we would start rejecting requests that you are expecting to be valid. We've seen this internally. You know, we give Bing a very strict adherence version of Kestrel, and an awful lot of their traffic dropped because it's not adherent. So, going to round up. This is our bug bounty program. I will pay you. Well, Microsoft will pay you, but I get to say pay this much, which is lovely. I will pay you if you report a vulnerability to us, and we agree that it is a security vulnerability. Please do not do this in GitHub issues. If you do it via GitHub issue, I cannot pay you. Legal will not let me. You need to report your vulnerabilities and security bugs to MSRC. The link is there. It's a lovely form. And if you do, like I said, I may have to write you a check. And yes, that is spelled correctly, Americans. The link here is for the core bounty program. You get to see how much we will pay out, minimums and maximums. Just make me happy. Let me write you a check. Let me spend Microsoft's money. Thank you very much. And don't forget, now that .NET 10 is out, you have a year left of support for .NET 8 and .NET 9. After that, no more security patches. Start upgrading your stuff, please.